All right, hello everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to another brand new exciting episode of Quirkcast. Before we get started, a few logistical things as usual. If you're on the YouTube channel, please post any questions or comments that you have during the episode, and we'll get to them. In addition to that, do join our Discord channel if you haven't already, so you can ask questions there, and we can also get to them as well. So without further ado, let's get into it. So Tim, I was thinking like it'd be really nice to be able to visit like the nearest galaxy and back super quickly. Is there a way I can do that? Or how would I achieve that?
Yeah, I think so. Two things, okay. So technically, if you have galaxies that are really far away, and using the most conventional way of traveling, let's say on a super fast spaceship in the future, it will just take, well, at least on Earth time, it will take a tremendous amount of time. But of course, because of Einstein's theory of relativity, if you travel at such a tremendous speed, right, relative to Earth, to you, it's possible that, even though Earth time has elapsed a long time, Sahil, you can still, maybe you only experience a very short amount of time, for example, traveling to a distant galaxy. Of course, that's sort of the conventional answer, right? But there is an alternative possibility. I think that came out when I actually don't know when. Right? There's some very intriguing solutions to Einstein's equations, and these are called wormhole solution. It's the possibility that you could kind of imagine like a little shortcuts between different points of the universe where you may be able to traverse, but this is highly speculative.
Do we have to do the Interstellar explanation of the wormhole? The one where they bend the piece of paper in half and then they the hole.
Is that where you have like two dots on the end of a sheet of paper and then you just simply bend them together so then the two dots are touching? And you say, oh, this is a wormhole, so you can get from here to here, versus having to go all the way around.
It's really an exquisite metaphor, actually, I think. Because people have all kinds of metaphors to explain things, but this one is like very genuine in terms of the geometry. I don't know if anyone's ever read the book Flatland, but there's a book called Flatland about like beings who live in two-dimensional surfaces, and life is very annoying there because you can't go over things. You have to go you can only go around them. It's like being in a 2D video game,
So then my question is like, what's stopping us from doing this, or like why hasn't this already come about? What's the issue?
Yeah, I think the issue is.
Yeah, quick answer. I mean, it's literally just a technological limitation. In order to create something like this, it requires a tremendous amount of energy. So if you think of like Einstein's theory says that space-time, you can think about it like kind of a flexible sheet. You can stretch, and you can compress it, but it actually takes a lot of energy to stretch and compress it. It's a very stiff sheet. So to make a wormhole would require you to, inject a tremendous amount of energy into small points in a very constructed way in order to connect them.
Yeah, so let me just add that there are actually two types of wormholes, kind of, if you can categorize it that way. So the first type that, in the sci-fi movies like Interstellar, those are traversable wormholes. So these are kind of highly curious mathematical solutions, and most of them require some sort of exotic matter, like things with negative mass, which we have never seen before. And it requires some sort of like a negative pressure, something like that. And that we don't know if it's even theoretically feasible yet. So those are traversable.
Wait. That's only to generate them like from scratch in nature, right? But there could have been pre-constructed wormholes.
Well, also to sustain them, I think, in order for them to be stable and not just this self-destruct. I think that also requires some exotic matter, and in fact, I think there's some papers that conjecture that space-time is kind of like that. It's like a self-protective. It always forbids traversable wormholes. There's some conjecture like this, but we don't know the answer yet, right?
Yeah, I mean, who knows what kinds of things could live, like, if wormholes do exist and we do live in higher dimensions, it's very possible that, the kinds of things we see could be restricted to just our part of that higher dimension. So I don't know. I think I like to think that there's, some reasonable possibility that these kinds of wormholes could be kept stable by magic. Understand.
I would say there's a slightly less controversial type of wormholes that we know the solution can exist without support, and these are called the Einstein-Rosen bridge. I think what ER bridge basically. So what they are is if you kind of
wait, they're not the same thing. I thought that
no, they're not the same thing.
Oh.
No. So they're different. So Einstein-Rosen bridge is a genuine solution to Einstein's equation, and it's a wormhole. So if you have a bird's eye view looking at space-time in some ways, which is not possible, but like imagine you have some kind of bird's eye view, you can see that it connects to different patches of space-time. But then you cannot go from one end and escape to the other end. What you can do, however, is imagine Sahil. You say, hey, Tim, let me meet you really far away in that galaxy. What we could do is we can coordinate, and maybe I'll wait for like a really long, let's say I wait a really long time, but like millions of years, maybe roughly I know how long Sahil will take to go to that galaxy, right? What we can do is I can time it, have a calculated the whole path, kind of coordinate with Sahil and be like, hey, Sahil, I'm going to jump into my little black hole here. So Einstein-Rosen bridge is part of a black hole solution. And I say, let's say imagine I know there's a bridge from black hole A to black hole B, right? And I can tell Sahil like, hey, I'm going to jump in here at this my time or my watch, right? And we can coordinate. We can coordinate in such a way that many years later, whatever, I jump into black hole A, Sahil jumps into black hole B, and we meet. That's the kind of bridge that we have. These are wormholes. They're not traversable. So I cannot, because remember, once you're in a black hole, you can escape, right? So what I can do is I can go in black hole A, Sahil can go into black hole B, and we can kind of mingle and be like, hey, Sahil, how was your trip? It's been a while. And and eventually we'll all be doomed, hit some kind of quantum singularity, whatever, or maybe we'll emerge somewhere else. But that's the type of slightly less controversial wormholes that are I think they're more accepted to exist. I think, right? Although we don't have obviously physical proof.
That is a wormhole. I think we shouldn't think about, that's when people say wormhole, right? That's really what they mean, right?
Well, it's not the Interstellar wormhole. I guess it could be. You won't be able to come back. I don't want to spoil the movie for anybody. But you're just stuck. You can't.
No, they didn't come back though. They didn't come back through the wormhole in Interstellar. They did send somehow they sent some correlations back, but that's possible.
Yeah, well, okay. Let's not spoil the movie, I suppose, for our audience. But that's the sort of wormholes that are more common. So let's be more specific. These are Einstein-Rosen bridge. So they're a particular type of wormholes.
So Tim, you mentioned the word genuine solution. Like, are all the other solutions just like not truthful, or like what would you say?
Because, as I mentioned, they require some weird matter, like either negative pressure, negative mass that we have never seen before. But the Einstein-Rosen bridge just requires good old vacuum. You don't need anything. And of course, to create it, you need, like Mikey said, it will be tricky. Once you create it, it's all good. It's stable, nothing crazy. So
I think that's the only kind of thing we should think about as a wormhole. I mean, like, what's the difference, right? So you can't actually go from one point of space to another, because as Tim mentioned, both people who fall into the black hole are destined to hit the singularity, but there's no saying how long that takes to hit the singularity. You know, it could be infinitely far in the future from your perspective. So, yeah.
Whoa. So no one knows how long it takes to hit the singularity inside of a black hole.
Not from the insider person's perspective. You can calculate it from the outsider person's perspective about some fictitious notion of what the insider person should be experiencing based on what you think is going on there. But I think all of or a number of recent results in physics have showed that the outsider's expectation of what the insider is experiencing is not valid in any sense of the word.
I see. So wait, like this Einstein-Rosen bridge would be between two black holes. Is that correct?
Yes.
A double-sided black
Okay.
hole, we sometimes call it.
Okay. So that's the most genuine solution. No one has found any like wormholes that just exist somewhere in space-time or just mad chilling. I don't know, just maybe around Saturn or something.
Yeah, we definitely have not seen any evidence of wormholes because, I mean, for one thing, all the black holes, the only way we see black holes are because of the, super, gamma radiations or gravitational waves emission from mergers. We have no way to probe the interior of a black hole.
Can I tell you why I think this is very compelling, though? It's because there's a lot of space inside of a black hole. I mean, we don't really know what's inside, as Tim said, no one can say for sure what's inside of a black hole, but it seems like you can fit a universe inside of a black hole. So if an Einstein-Rosen bridge is just connecting two black holes together, it's kind of like connecting two universes together.
Wait, what do you mean? Like you're able to fit a universe inside of a black hole? Like to our audience, can you explain? Because typically when you think of a black hole, you think of this like black sphere, and that's it. And like, how do you fit a whole universe in there?
Yeah, I can't give a precise answer because the precise answer is not known. But like, there's a couple of hints that we have about that that I think are intriguing, at least.
Yeah, I mean, theoretically, you can imagine if the universe was not expanding, theoretically, you can have a black hole that can eventually suck up the entirety of the universe. So in that way, you can imagine, let's say Tim falls into a black hole at some time, like eventually the entirety of the universe is gonna go in the black hole. So to some extent, all the information that ever was will be eaten up by the black hole.
Or if not eaten up by it, eventually be entangled with it in a very specific way.
Yeah.
So I mean, even from the classical perspective, right? Like, so people describe like the popular way to visualize the event horizon is like a waterfall, right? There's a point of no return on the waterfall, right? Like you can swim away from the waterfall. If you're a strong swimmer, if an inhumanly strong swimmer, you can swim away just up until the edge, right? But after that is the point of no return. After that, there's some intense stretching going on inside the black hole that, is the reason why we call that the boundary, is the point of no return. So that intense stretching is very real, regardless of whose perspective you're looking at, from the insiders or the outsiders. So it seems like that's the point at which space is being made at a very fast rate inside the black hole, if we're talking about space as being stretchable. And the other thing we know is that the outsider's perspective, as we mentioned, is not a good description of what the insider is experiencing. And a lot of recent papers have shown that actually it's probably radically different. What the outsider sees and what the insider experiences is probably very, very different, like almost as different as like translating between two programming languages, the same instructions. Or a translation of two languages. There's some kind of translation that occurs at the boundary. So there's a lot of space in there for the imagination to play games with what could be experienced by the person falling in.
Wow. So, going back to wormholes, if you haven't observed them in actual space, and the only genuine solution exists in black holes, do they exist at all, or are they just kind of a fancy?
Yeah, well, we don't know of any evidence that they exist, but I think there's a theoretical. So imagine we have infinite resources. There is potentially a way we can genuinely create one, and it goes like this. Okay, and this will probably lead to additional questions. Okay, it goes like this. Imagine you create a super high energy accelerator, right? And then you smash, I don't know, some particles. Let's say you smash light particles together, and it creates positron and electrons. They're antiparticles of each other. And when they're created, they're fully entangled, let's say. And what do I mean by they're fully entangled? It means that if I know all the information of one of the particles, I also know the full information of the other particles, right? So it's like a twin, but better. They're like completely in tandem, their motions, so their properties, right? So imagine I create many of these, right? I imagine I create a bazillion of these pairs, and I use my technology machines to gather all the positrons in one side and all the electrons on the other side, and collapse both of them into a black hole. Okay, so now I have black hole A, which is made of positrons, and black hole B, which is made of electrons. Okay, now in this really strange scenario, you ask, well, why the heck do we care? Well, we care because these are fully entangled, right? So imagine this. Imagine Tim falls into black hole A. It's filled with positrons and kind of mingle around with those particles there, right? And Sahil, you fall into black hole 2. You will fool well because they're entangled. You will have full knowledge of how Tim is mixing up those particles, right?
Yeah.
And now you go through this logic now. If Sahil sees what I'm seeing in some ways, it looks exactly the same in some ways. And depending on how I mingle it, Sahil sees exactly how it looks like. And if Sahil mingles with the particles, I also see it. If it quacks like a duck, it looks like a duck, it walks like a duck, the two things must be the same. So it really means that if I fall into black hole A and Sahil falls into black hole B, we're actually in the same black hole. We're in the same, well, maybe I wouldn't say black hole. We're in the same piece of space and time. This situation happens to coincide with, we mentioned earlier, the properties of an Einstein-Rosen bridge. I go into one black hole, you go into another black hole, and we meet and we can hang out, right? So this thought experiment kind of illustrate how to perhaps really create one of those. Maybe they really exist.
Do you need to collapse the positrons and electrons into black holes, or could you just keep them as kind of this like thing by itself?
I think because they are entangled, the moment, like if they remain entangled, the moment you collapse the positrons into black holes, the electrons will automatically collapse into black holes.
No, does that have to be true? I don't know if that has to be true. I don't think so.
I think.
I think no, they don't have to. Yeah, because it's as entangled as a one-sided black hole with a Hawking radiation, right? Like it doesn't matter who collapses the black hole first, right? Whoever's in possession of this collection of particles will still be able to know what's inside the black hole, right?
I'm not sure. The amount of entanglement would change if you don't do it perfectly symmetrically.
But not the amount of entanglement between the two sides. That would remain the same regardless of what. I think it's supposed to be equivalent, whether or not.
No, it raises a good question, right? This is sort of follow up to the theme of this episode. Like the kind of final structure of the black hole depends on the entanglement structure, right? Like if somehow I took the positrons and I unentangle them and I entangle it with something in the environment, and when I collapse the two black holes in, there wouldn't be there wouldn't be a wormhole anymore, because as I tweak, imagine Tim falls into black hole 1, and I tweak the particles inside the black hole 1. That information will not be encapsulated by the other set of particles, because you remove the correlation, right? Somehow. So the structure.
Like a person with like you could collapse Sahil's black particles into a or Sahil's side into a black hole. Sorry, you could collapse the electrons into a black hole.
But if they're not entangled,
a person who could descramble those it would be equivalent to being inside the black hole. It's still a descrambler. Yeah.
Right. I mean, maybe you don't have to collapse both into black holes, I suppose. It could be one black hole and then entangle with a bunch of particles that are not yet.
It would just take work on the other side, as much work as it would take to make a black hole.
Yeah, I mean, you don't have to make two black holes, I guess. Yeah, then there wouldn't be an Einstein-Rosen bridge. But if you do make two black holes,
yeah,
then it will make an Einstein-Rosen bridge.
Yeah, it has to be two black holes for it to be an Einstein-Rosen bridge.
Right, yeah.
But not to meet again.
Yeah. So this thought experiment is extremely interesting now, because on the one hand, we have general relativity, talk about Einstein-Rosen wormholes, black holes, and all that, right? There's nothing quantum mechanical about it. These are just like, think of them as space-time getting stretched out, connecting to one another, right? There's nothing quantum mechanical. It's just like a stretchy space, right? But then now, all of a sudden, once we add quantum physics, this concept of entanglement, and that somehow becomes related back to the structure of space-time. Now that makes it very interesting.
What do you mean it relates back to the structure of space-time?
Yeah, so I think, well, going back to this thought experiment again, right? If two things are entangled and we collapse both sides into a black hole, the entanglement causes the two black holes to be connected by an Einstein-Rosen bridge, right? That tells you that, imagine that was true, right? Then it kind of begs the question, is the converse also true, right? Like, are they really, maybe they're equivalent, right? So maybe wormholes are just ways of entangling each other, and maybe wormholes are just part of quantum physics. And I think this was one of the breakthrough conjecture. It's called the ER equals EPR conjecture. It's a bit complicated, but it requires further elaboration. Let's put it at that.
In its full glory.
How do we know that our universe isn't the one that was made out of all the electrons, right? And we're entangled with some positron universe that's like far away. Very real possibility.
Huh. Are you saying that we're entangled with another universe that's like all antimatter instead?
Could be.
Or more exotic, right? Like Sahil, you here is entangled by some. Like, first of all, Sahil, you might be entangled with some. I don't even know. I wouldn't call that Sahil, but just some collection of stuff.
Yeah.
Outside our observable universe, right? Right, and because you're entangled with it, you're also connecting to them through wormholes. So and this is just kind of mind-boggling, right? We could be entangled with a bazillion of different things, and the way we entangle with them is because of these, it's because of these little mini wormholes, basically. Yeah.
Yeah. In fact,
so would you say like
intriguing results? I don't know if I can reproduce them exactly, but I know that there's a kind of a special number that's kind of intriguing that, if you assume that all this stuff is true, right? That like all of these principles we're talking about can be taken seriously, then if our universe can be thought of as a black hole, and if we are connected to stuff outside of it, at least three separate people need to be able to reconstruct me, like my body, for example, outside the universe, there's actually a redundancy in the description from the inside to the outside. So it's not just good enough that if our universe is a black hole, and if I'm inside that, it's not just good enough that someone from the outside can, descramble me into existence. Three separate people on opposite sides of the universe need to be able to descramble me. Apparently, the laws of physics require this kind of like redundancy, like 3 copies of me need to be reconstructible.
Not 2, like only it has to be 3.
Yeah, the Qtrit, there's the 3-bit example is the minimal working example that reproduces the laws of gravity that we understand if you take this model of the universe seriously. That the inside of the black hole is separate from the outside, and there's some translation happening when you cross the border.
So Tim, going back to your point, like, is it possible for there to be like a voodoo doll that's entangled with you, and if I like do something to this voodoo doll, it'd do something to you, or based on this wormhole entanglement business?
Very anthropomorphic, right? I mean, we said positrons, like there could be an antimatter universe separating us. That's like the simplest possible example, right? Like probably the reality is like something crazy we can't even imagine, like infinite dimensional chess or something.
Yeah. I mean that's sort of the idea, and of course in reality it's really difficult to maintain that level of entanglement. So going back to that picture, in order for the two things to be equivalent, where entanglement is the same thing as black hole, right? Going back to the example, it basically sprung from the idea that, hey, when you create the Einstein-Rosen bridge, in that thought experiment, you need to collect all the particles together so that both sides collapse into a black hole, right? That's what you need to do. And the leap of faith is that, imagine maybe all the entangled particles individually already had like a tiny little Rosen bridge, like a quantum mechanical Rosen bridge. And by collapsing them into black holes, you're merely merging those tiny little Einstein-Rosen bridge to cause into a bigger Einstein-Rosen bridge, right? Right? If that image was true, then yeah, it's quite likely that me might be entangled with maybe not voodoo dolls, but like I might be entangled with the environment, particles maybe outside of our universe. And literally the voodoo doll string, this ephemeral string, is just like a little microscopic, well, smaller than microscopic, this Einstein-Rosen bridge that kind of tugging me along, right?
Like in Interstellar.
So one question I have is, like, you mentioned this thought experiment of taking particles that are extremely entangled with each other, collapsing them into black holes. And suppose I do that, and these two things are entangled with each other. Is there like certain disturbances that can naturally occur that would disturb that entanglement even after you've collapsed into the black holes? And just like the environment itself just existing?
Yeah. I think everything in general.
Say no. Like, I mean, within those black holes, the entanglement exists. I mean, Hawking radiation would be the only thing, right? If these black holes are radiating, then that could mess up the entanglement, make it go somewhere else. But if we're talking about two black holes entangled with each other through this process, then what's inside the black hole stays in the black hole, then that entanglement is exact. And I think that's the reason for the thought experiment. It kind of simplifies the problem, right? If I just imagine that both of these things are black holes, I know that these two kind of mystery boundaries are connected with each other, through some backdoor.
So one question I have is, like, in this experiment, suppose we create these two black holes that are entangled with each other. I jump in one, Tim jumps in the other, but Tim and I are entangled with the environment. So we jump in the black hole being entangled with the environment. So how does that work if Tim mucks with things around in there? Like, will I see a similar thing, or
Yeah, I would say if you and I are entangled, let's say in some weird way, then we will contribute to that Einstein-Rosen bridge, right? As we fall in, we kind of, and if we are entangled with something outside, I think the Einstein-Rosen bridge structure would be quite different. Is it possible to have like multiple forks of these Einstein-Rosen bridge? That I'm not sure.
I think that's actually the crux of the firewall paradox, is that if you assume that you and Tim are maximally entangled, then it can't be that, like, how does the entanglement get transferred to each other if you go into these two black holes that are not, you know, supposed to be, if they're supposed to be independent of each other, right?
Yeah. I think if we take this conjecture literally, then there should be like a fabric, a network of these Einstein-Rosen bridge everywhere, right? Like if I'm entangled with some environment, I fall into the black hole, then the black hole will have some network of Einstein-Rosen bridge connecting to every different pieces. And some of that will connect to a different black hole. And then also there will be some network, you know, connecting to these particles. And maybe, in fact, maybe if you take this leap of faith even further, like maybe that's what space-time is. It's just networks of, you know, Einstein-Rosen bridge. Maybe that's more fundamental.
Oh yeah, no, that runs. Yeah, actually, I saw what the answer to that question actually is. Yeah. So if you and Tim actually fall into the black hole and you are entangled, so this only works for infinite black holes, but you and Tim's interaction as you entangle inside this Einstein-Rosen bridge, if you imagine infinitely far into the future, it actually loops back around to the past. So it's like your interaction inside the black hole is related to your prior interaction that made you entangled in the first place.
What? Wait, so you're telling me that there's some time traveling stuff that's happening?
The easiest, no, not time traveling. I'm just saying that the simplest example of what Tim is talking about was first shown for eternal, I mean, like infinitely lasting. I mean, they never radiate, they never go away. Infinitely lasting two-sided black holes. You can show that the infinitely far future is actually looped back to the infinitely far past. So if you're trying to explain why you and Tim are entangled and how that got to be, that can be explained by connecting those two points, the infinitely far future, the infinitely far past. Those are the only 2 points that are connected. You can't choose which one.
Whoa.
Yeah.
I see. So we are running up on time. And so do you guys have any concluding thoughts before we head out?
Wow. Yeah, it's a very,
so.
I guess I can go first. It's a very intriguing possibility, and obviously there's still a lot of research into it, and it's highly speculative. It may or may not be true. But given that we don't understand what the fundamental nature of space-time is in a quantum mechanical way, like this is a very real and intriguing possibility. And because these thought experiments, they're very clever. I mean, these are, I mean, I didn't come up with them. I think it's, you know, like Leonard Susskind at Stanford, or like Juan Maldacena. These are, and probably missing many. These are the pioneers of our field, thinking about these thought experiments and making these really bold and incredible conjectures. And I think there's a real shot of them being real. You know, like this could very well be part of the, I guess, the fundamental nature of reality. I don't know. It just kind of changes the way you think about things.
Yeah, just to continue on that, I think the writing's on the wall, right? Like, so these ideas maybe 5-10 years ago were considered like very fringe. Even though the top people in the field were the ones pushing these ideas, it was still so out there. These ideas seem so crazy. But I think now in the last, at least especially 2 or 3 years, all of the evidence, all of the thought experiments done by so many different people are kind of pointing towards the same thing. And so at this point, as a physicist, you just kind of, you know, you put your money on what's the smart thing to think about, or at least invest your emotions in. And I think this is it.
Well, on that note, I think that's a great place for us to end. So on that note, I'd like to thank everybody for joining us.
All right. Yeah. Thanks, everyone. See you guys next time.
See ya.
Bye.